Alright, so for today's lesson, we'll be entering the last lesson for chapter 4, which is discrete random variable, and today we'll be covering up the last learning outcome, which is how to calculate the expectation of geometric distribution. Okay, but before I move into that, I would like to make some further explanation on the thing that we learned in previous class, because this is the last lesson that we will be doing for this chapter already. Then for next week, we're entering chapter 5, which is the last chapter for your statistic. Alright, so for today, I would like to calculate and try to connect everything together so you can have a better understanding that what are we actually learning for this whole chapter. Okay, so you see the big topic of this chapter, right, is actually called as discrete random variable. Okay, so you see we have a total of 6 lessons for this chapter, and the first 2 lessons we learned about discrete random variable. Then after that, we know that discrete random variable is basically a variable that you can take on any number, but as this is discrete, so that's why you can take on like certain value and exact value that actually randomly occurs in an experiment. Okay, so meaning that your result must be an exact value. Normally it will be a countable one, or like 1, 2, 3, 4, 5 and so on. So those are discrete random variable. Okay, so under discrete variable, we learn what is like probability distribution, like how do you create a table or a listing with all the possible outcome of your discrete random variable, then how to find the corresponding probability. Okay, so you learn how to do probability distribution. Okay, then after that, you also know that for discrete random variable, right, you also know that how to find your expectation and how to find your variance. Okay, so if you still remember, for your probability for a discrete random variable, then your expectation or your mean will be equals to sum of x times the corresponding probability. Then after that, you also know that for variance, okay, then it will be for the variance part, then it will be equal to the sum of x squared times your probability and then minus your mean square. Okay, so this is what we learn for discrete random variable, which is our first 2 lessons. Then after that, we learn about binomial distribution. So under binomial distribution, right, you learn how to find the probability, and the most important thing is you know what is the constraint for a binomial distribution. And then after that, you also know how to find your probability, which is by using Px equals to R, then NCR, PR, then Qn minus R. Then after that, you also know how to find your expectation, which is your mean also. It will be equals to N times P. Then after that, you learn how to find your variance, which is equals to NPQ. Okay? So then after that, we also know that for the last part, you learn about geometric distribution, which is our lesson 5. Then after that, same thing, you also know what is the constraint for your geometric distribution, and then you also know how to use formula to find your probability of a geometric distribution. Okay, so which is P Q, then after that R minus 1. Okay, so this is what you have learned like throughout this chapter. Okay, so I want to explain about something. So you see, these are the 3 things that we learned. So you see, right, my question is, of course we know that in discrete random variable we have a lot of like distribution. So binomial distribution and geometric distribution is one of the distribution that actually specially produced in discrete random variable. So you see, when we learn about discrete random variable, right, we don't have any constraint. We learn it is like a general idea of this is like a variable that you can randomly occur as long as it's a discrete data, then we can put it in a probability distribution. So you see, this is like a big idea. Then after that, under discrete random variable, we know that some of the situation we can actually produce some special distribution. So that's why you have like binomial distribution and you have like geometric distribution. Then of course you have actually a lot of more. So meaning something like Poisson distribution, something like hypergeometric distribution, or like even you have multinomial distribution and so on. So those are the distribution of a discrete random variable also. It's just that we are not learning it in our A-level S1 syllabus. So you must know that not every discrete random variable is a binomial distribution. Not every discrete random variable is a geometric distribution. Only discrete random variable that satisfy the constraint for binomial is called as binomial distribution, and those satisfy for geometric distribution is called as geometric distribution. But my question is binomial distribution, geometric distribution, and Poisson hypergeometry, everything here is considered a discrete random variable? Yes. So if they are not discrete random variable, then they even cannot satisfy the first basic of the distribution already, which is it must be a discrete value. Okay, so meaning that if we are talking about that, right, so meaning that for everything that you can do in your binomial and geometric, you must can be done by using the formula for probability distribution also, because everything is under this, like these are all subset of discrete random variable, but only certain thing that you can satisfy the constraint is called as binomial or geometric. So meaning like for let me give you an example. When I talk about discrete random variable, right, let's say if you have something like I have 5 balls in a basket, so meaning I have 2 red balls and 3 blue balls. Then after that, I'm going to pick it from the basket. I'm going to pick 2. But then the idea is I want to find the number of red balls that I pick. So of course you can know 0, 1 or 2 that I'm going to pick. The possible outcome is 0, 1, 2. But after that, my idea here is like after I take it, I do not want to replace. So you see what happened is every stage my probability is going to be different, because when I take out one, my sample space become 4. When I take out another one, then my sample space become 3. And whether I pick a red ball or I pick a blue ball is going to affect my next outcome of my probability. So you see, for every stage here is not independent. For every stage is not going to be the same probability. So these are something that not satisfy your constraint for binomial and geometric. So that's why in this situation it is a discrete random variable, because the possible outcome is 0, 1, 2. But then it's not a binomial distribution and geometric distribution. Okay, so I hope you can get it. Like actually discrete random variable is like the whole idea, but then for binomial distribution and geometric distribution, it's like some special distribution that can produce with certain constraint of your experiment, then only you can produce binomial distribution or geometric distribution. So that's why if you have something that asks you like whether this set of data or this experiment fits into binomial distribution or not, the idea will be like you need to check on the constraint, and you need to check on when you do it with your mean or with your variance, are you going to get the same thing? Okay, so maybe I try to do like one very simple example here so you can see like because I think I didn't really go through the idea of proving when we do the expectation and the mean and the variance for binomial distribution. So I'm just going to bring you through a very quick example like as what I have explained here. Okay, so you see, now I try to do something like this. Let's just use a very simple example here. Okay, so X is a binomial distribution with a parameter which you have a number is 2 and then 0.6. Okay, so let's try to create the probability distribution. Okay, so we have X, then we have P, X equals to X. Okay, so my possible outcome is only 0, 1, 2 lah. Okay, so this one will be NC0 and then P0, Q2, NC1, QP1, Q1, NC2, P2, Q0. Okay, so I'm just going to count it like very quickly. So you can use your calculator to get the answer, but I'm just going to write it down. So to make it quicker. Okay, so what I'm going to show it is just now I said that for binomial distribution and geometric distribution, it's a special distribution under discrete random variable. So if we say that these two are the subset of discrete random variable, meaning that we must be able to get the exactly same answer no matter we use this formula or we use this formula. So you see, since that you have different formula for discrete random variable, right, for expectation and for variance, so I have another one for binomial also. So let's see, if you're trying to use the binomial equation, the formula under binomial distribution, right? Okay, so how do you find the mean? So the mean will be equals to NT. So how do you find the N? The N will be 2. The probability is 0.6. So you have 1.2. Then after that, for your variance, then it will be equals to NPQ. So your N will be 2, your P, and your Q. So it will be given you 0.24, so 0.48. Okay, so you see, this is by binomial distribution. Now let's try to use the original formula. Okay, alright, DRV lah. Okay, discrete random variable. Okay, so you see, for me to find my mean or my expectation, which is the same thing, I will need to use the formula here. Okay, so you see, this is my probability distribution, right? So what do I have? So meaning that I will use 0 times 0.16 plus 1 times 0.48 plus 2 times 0.36. And after I press calculator, right, I will get the exactly same answer like the binomial distribution. Okay, let's say I am going to do my variance. Okay, so my variance will be equals to the sum of every x squared times p, then minus the variance that I have. Minus the mean that I have. So meaning it will be 0 squared 0.16 plus 1 squared 0.48 plus 2 squared 0.36, and I will minus 1.2 squared. So from here I'll be getting everything I plus together, then I get 1.92 and then minus 1.44, which will give me 0.48. So you see, it's exactly the same thing. So from here you can see that for binomial distribution, right, why are we using NP and NPQ instead of this? Because you see, it's exactly the same answer, then why not we choose the one that we can? So you see, when we learn about binomial distribution, right, I try to what is that called, explain to you like why is that so for every variable, like what is that mean by your mean, what is that mean by your variance, and so on. So you see, by using binomial in a very short way, you can actually get the answer by using something like what is the real meaning by expectation and the variance. So that's why we are not using this. But can you use that? Yes, why not? Because binomial distribution is one of the distribution produced by the discrete random variable. So anything that you use binomial or you use geometric, right? If you're not sure that the question is asking is a binomial or a geometric, and they want you to find expectation and variance, then you can use discrete random variable because everything is under discrete variable. So that's why you can solve everything by using the by using these two formula. Okay, then after that, you see my question is, if all binomial can use discrete random variable, can all discrete variable use binomial? No. So if you have something like the situation that I said just now, the ball and the basket, that one. So if you have something like that, meaning that when you do your discrete random variable, then you use EX and variance, then of course you can get the answer. But you cannot use binomial distribution because you do not have a constant P and you do not have a constant Q as well. So for things like that, then meaning that it is a discrete random variable, but then it is not a binomial distribution. So meaning that the data is a discrete random variable, but then it doesn't fit into a special distribution, which is called binomial distribution. Okay, so I hope that you can understand this whole idea, that it will be helpful for you to like move on to like why is that like so many distribution under this. It's like some of the special pattern or some of the special distribution that can be produced by a discrete random variable. Okay, that's it. Okay, all right. Okay, so now we will be entering into the last learning outcome. Okay, so before we move into that, some recap for geometry distribution. So the constraint or something that you must be achieve or you must be following when you want to say that the discrete random variable is a geometric distribution is that you must have infinite number of independent trials. So your trial must be independent, and because you want to get the first success, so that's why you cannot have a limited number of your trial. Then after that, your trial must have only two possible outcomes, which is a success and a failure. Then the probability for each stage of your trial must be a constant one. So for geometric distribution, you also know that the probability that your first success occurs on the R trial is going to be PQ to the power of R minus 1 lah. Okay, so I'm not going to like go further into it. So make sure that you finish your exercise and a video for lesson 5 before you watch this. Okay, so before I want to talk about expectation, let's talk about some very brief features for geometric distribution. Okay, so look at your notes. Yeah, so I'm not going to like ask you to draw and everything, so this is like not the main part for the lesson. So I'm just trying to explain it so you can understand everything instead of like in case of that is question that asking about your understanding and so on. Okay, so for every geometric distribution, right, they will have two features in common. So which is the first one is the probability for x minus 1 is always the one that having the greatest probability in all this geometric distribution. So meaning that the most likely value of x will be 1. So the idea of it is like the first success of an geometric experiment is most likely to occur on the first trial. Okay, later we'll be looking at the example. Then after that, the value of your probability decrease when your R increase. So meaning when your number of trial increase, the probability for you to get the first success will be decreasing. Okay, I mean it's very common sense because what you are saying something like first success. So the idea of it is like then of course the most likely occur will be on the first trial, then this is how you get the first success. So as you continue, you accumulate like a lot of more and more failure, so that's why the probability for you to get the first success will be like decreasing. So you can see for these two examples, so I pick one that is like the P is below than half and a P is greater than half, which is 0.6. So when you look through this set of value, you can realize that for Px equals to 1, they always have the highest value. Then after that, you can see all the value here is decreasing, then all the value here is decreasing also. So when you look it, when you try to look at it with a bar chart or even with a vertical line graph, you will realize that for geometric distribution, right, they will always have this kind of graph, which the graph is like decreasing. Okay, and you can realize that for everything here, actually I do not have an upper bound. So meaning that what I can do is I can of course continue, because I do not sure that which outcome I will get my first success. So meaning this graph can be continuing, but it will be decreasing and nearer and nearer to zero without being negative. So you can see, like for this one, right, it's basically later when we prove about the expectation, you will realize that we were touching on something that is called geometric series or geometric sequence that you actually learn in your progression, your GP, geometric progression. Okay, because like this is something that is the same thing like your R. Everything that you are trying to do is like from the first success to the second success is like you times one failure. From here to here, from 2 to 3, then you're going to times one failure again. So like you see, for your Q, right, your probability of failure is of course an R, a ratio that is actually smaller than 1, which that satisfy your idea of like how to when you the idea of you have a convergence series in your geometric progression. Okay, doesn't matter, you don't need to know about that. What you need to know is you just remember that for geometric distribution, your px equals to 1 will have the highest probability. Then as your number of triad increases, all your probability will be decreasing. Okay, then after that, now we'll be looking at some proving. So for the last part, for the MP and MPQ, I did not do that because I think it will be easier for you to understand why are you doing so. But for this one, I realized that it's quite hard for me to like explain why are you doing 1 over p for mean. So that's why I'm just going to do a very quick proving. So but as you see, for your learning outcome, right, your proof of formula for expectation is actually not required here. But it's just that like for normal lesson lah, what I'll do is I'll try to explain how the formula come from and so on. So I'm just going to do a very quick one for this one because that's not the main idea for the lesson. So the main thing that you're going to learn is how to use that. Okay, so I'm just going to do this like very quick. Okay, so let us try to write out what is the write out the probability distribution for this geometric distribution first. Okay, so if you have x equals to 1, then you will have p. If you have x equals to 2, then it will be pq. Then you will have pq squared. Then you will have pq cubed. Okay, I hope that I do not need to explain further about that. Okay, so recall from what we have learned previously, right? We say that binomial distribution and geometric distribution are the special distribution under discrete random variable. So that's why for this one, we are going to use the formula under discrete random variable, which is the ex will be equals to sum of x times p. Alright, okay, so for geometric distribution, you realize that for your learning outcome, you are going to learn expectation only. So meaning that there is no variance for geometric distribution. I mean, there is a formula for that, but you are not learning it in S1. Okay, alright, so the expectation, it will be the sum of x times p. So you see, for binomial, you have a finite number of triad, means you can plus everything together. But what is the problem of a geometric distribution? Is that you do not have a finite number of your triad. So that's why when you try to use this formula, you will realize you have something stuck in the middle. So you see, expectation of x, the mean of x will be equals to sum of xp. So meaning that what you will do 1 times p, 2 times pq, and then after that 3 times pq squared, then after that 4 times pq cubed, then continue on. Yeah, because this is infinite number of triads, right? Okay, then after that, what am I going to do next? So with this, I cannot write my number like that. Okay, so what I'm trying to do is this will be my first equation. I'm going to come up with second equation that I can solve with it. So now what I'm going to do is for everything here, I'm going to times with Q. Okay, so meaning 1p, then it will be 1pq, then plus 2pq square, plus 3pq cube, plus 4pq power 4, plus and so on. So this will be my second equation. Okay, now what I'm trying to do is I will use my first equation to minus my second equation. Minus my second equation. Okay, so it will be expectation of x minus q ex. Okay, first equation minus. Then what do I have? 1p, I do not have anything to minus in common. Then 1p. 2pq, when I want to minus, then 2pq can minus 1pq, right? So it will be 2pq minus 1pq, then I get 1pq. Okay, then after that, what do I have? 3pq square and 2pq square. So meaning that it's like this. When I want to minus, it will become something like this. So 3pq square minus 2pq square, which will give me 1pq square. Then 4pq cube minus 3pq cube, it will give me 1pq cube. Plus, then you know that the next one will be like pq4, pq5 and so on lah. Okay, so this is what I get. Okay, so now let's try to do some factorization. So you can see what happened here. I can always take out my expectation of x, then what I left in common is like 1 minus q. And after that, for every term of this, I have my p. So p, then after that, I left with 1 plus q square plus q cube and so on. Okay, so what can you realize here is this part, 1 plus q square plus q cube and so on. This is actually a geometric progression. So what is that? Your A is 1. What is your R? Your R is basically Q. Everything you times Q, right? They have the common ratio here. And then this is an infinite number. So that's why when you want to find everything plus together, that meaning that you can use the idea of sum of infinity will be equals to A over 1 minus R. So we are going to use it here. Okay, so let's continue. 1 minus Q ex, then it will be equals to P. Then after that, what happened inside here is my sum of infinity. So my A is 1. My first term is 1. Then 1 minus R, my common ratio here is Q. So 1 minus Q. Okay, so now you see I do not have an infinite number, so infinite number some more. So I'm trying to put it in a sum of infinity. Okay, so after that, I'm going to change what is 1 over Q. It's basically P, right? So the same thing happened here. I'm just going to change 1 over Q to P. Okay, then after that you can see P and P, they can eliminate each other. Then I move my P over here. So this is how I get expectation of x will be equals to 1 over P, which is our formula today. Alright, yeah, so this is why we are not using the formula for discrete random variable to solve this, because you will realize that you have everything like infinite. If you are going to do that, meaning that you will need to do this process over and over again for all the questions. So that's why we just do it one time for general one, so you can get the formula. So that's why for every question, we are going to apply this formula only. Okay, so I hope that you can understand why are we using the mean or the expectation equals to 1 over P. So actually it's the same idea of discrete random variable. It's just that because of its infinite characteristics, so that's why it will make your life like very hard if you want to do that. So that's why we try to do simultaneous equation and solving and so on. It's just your AP GP which we use formula lah, so you are not going to repeat all the process that you used to prove the formula. Okay, so I also attach here. So in your exam, the formula will be given like that. So for geometric distribution, this is how you find your probability, then this is how you find your mean. Okay, so let's move on for some example here. Okay, so we have only 1, 2, 3, 4, 5 questions here, so we are going to do this very quickly. Okay, so number 1, if x is a geometric distribution with your p 0.8, find the expectation of your distribution. Okay, so this is very easy lah. So ex will be equals to 1 over p. So your p is 0.8, so 1 over 0.8. Okay, so which this question will give you an answer for 1.25. Alright, easy. Okay, B. So for P, probability for x smaller than your expectation. So your expectation here is 1.25. So that's why probability for x smaller than 1.25. So what is the discrete number that actually smaller than 1.25, which is Px equals to 1. Okay, so it will be equals to, what is that, 0.8. So which is the first time you already get your first success. Okay, alright. Okay, number 2, 1 in 2 boxes of Zingo breakfast cereal contains a free toy. Let the random variable x be the number of boxes that a child open up to and including the first one which they find their first toy. So find the mode and the expectation of x. Okay, so the mode, if you still remember, the mode is basically the measure or your variable that have your highest frequency. So when we talk about highest frequency, right, actually we talk about the most frequent one. So the most frequent meaning that the probability is the highest. So you still remember in geometric distribution, what is the one that have the highest probability, which is when x equals to 1. So please refer back to the first page of notes if you have forgotten this. So basically the mode will be equals to 1. Because the Px equals to 1 is the highest. Okay, has the highest probability lah. Okay, so let's move on. So how to find the expectation of x? Then it will be Ex equals to 1 over P. Okay, so what is your probability of success here? So it's one of the 4 boxes. So meaning that it will be 1 over 4 or 0.25 lah. Then you will be getting 4. Okay, so B, interpret the 2 values found in the context of this question. So this question I just added, so because I want you to understand what is the difference between the 2 value here. Okay, so when we talk about mode, right, then we talk about the highest frequency. So when we interpret mode, then we will say that a child is most likely to find their first toy in the first box they open. Okay, so this is what is that mean by mode equals to 1. So meaning the first box they open. So a child is most likely to find their first toy in the first box they open. Okay, so how about Ex? Ex is the mean, right? So we say that, however, okay, in average, the mean tells us about the average. So in average, a child find their first toy in the 4th box they open. So this is what is that mean by the mean or the expectation is 4. So meaning that although we know that in terms of probability, a child is most likely to find their first toy in the first box they open, but the expectation or the mean tells us that in average, a child only find their first toy in the 4th box that they open. Okay, alright, number 3. So the variable x follow a geometric distribution. So Ex equals to 3.5. Find Px greater than 6. Okay, so meaning that if we want to find Px greater than 6, then we know that for Px greater than 6, it's like your first success occurs after 6 terms. So meaning that you have 6 failure. So meaning that you need Q6. So for you to do this question, you must find out what is your Q first. So for you to find your Q, then you must need your P. So how do you get your P? You get it from your expectation. So EX here equals to 3.5 or 1/2. Okay, so EX is basically 1 over P, so equals to 3, 2. Then what is your P? Your P will be 2 over 7. So from 2 over 7, then you can get your probability of failure, which is 1 minus 2 over 7, which gives you 5 over 7. Okay, so how do you find that? So probability for your number of trials needed to find your first success is greater than 6. It means you have 6 times of failure. Then after that, 5 over 7 power of 6, which will give you an answer 0.133. Okay, it's just about solving equation. Alright, so let's move on. The last page. Okay, if X is a geometric distribution with expectation equals to 4, find the value of P. So EX equals to 4. So 1 over P equals to 4. So meaning P is 0.25. Okay, so B is the same thing, repeat again. So probability for X greater than your expectation is your expectation is 4. So the probability for number of trials needed for your first success is greater than 4, meaning that you must have 4 times of failure lah. So it will be equals to 0.75, or like in a better way, try to write it 1 minus 0.25 power 4. Okay, so you will be able to get 0.316. Okay, so B, the least integer n such that Px greater than n is smaller than 1%. So let's try to rewrite this first. So probability for x greater than n smaller than 1%, meaning 0.01. Okay, so for your probability for your number of trials needed to get your first success is greater than n. So if you still remember the last lesson that we talked about, this is basically same like this, so meaning that I can always change it to Qn. Okay, so meaning that the number of trials needed for me to get my first success is greater than n, meaning that before the n time I'm getting every time failure, so that's why Q power n, so smaller than 0.01. So my Q here is 0.75. So 0.75 power n, then smaller than 0.01. Okay, then after that I'm going to solve it and log again. Okay, so n, so remember log 0.75, since 0.75 is smaller than 1, so meaning your log will be giving you a negative answer. So that's why you need to change your sign. Okay, then I'll get n greater than 16.008, so my least integer here will be equals to 17. Okay, the least number that satisfies this value. Okay, so it's 17. Okay, number 5. So given that x is a geometric distribution with p, then this is your, what is that called? This is your probability when the number of trials needed for your first success is smaller or equals to 3. Then find out that one. Okay, so p x greater than 3. Okay, so for this one, what you can try to do is either you can try to find out your PQ, but then you see there's something common here. So if you want probability x greater than 3, meaning that you are finding 4, 5, 6, 7, 8, 9, and so on. Then after that, the question gives us the probability for 1, 2, 3. So what you can try to do is you straight away. So since you want to find the probability for x greater than 3, is actually equals to the complete picture minus the 1, 2, 3 that you don't want. Alright, easy right? So meaning you want 4, 5, 6 and so on. So meaning you minus the 1, 2, 3 that you don't want. So 1 minus 8, 1, 9 over 1, 3, 3, 1. So it will be equals to 5, 1, 2 over 1, 3, 3, 1. Okay? So for B, now when you want to find this, okay, So for this question, you might have like two scenarios here. So the first one that you want to do is because you want to find the x which is 2 and 3, like it's greater than 1 but it's smaller or equals to 3. So that's why you want to find x equals to 2 and x equals to 3 lah. So either you can do px equals to 2 plus px equals to 3, or the other way you can use this one. Since this give you 1, 2, 3 and you only 1, 2, 3, so meaning you minus the 1. But the idea here is no matter which way you go to, you must find your p and q. So that's why we need to use this or this to find the number that we need. So let's use the one that we found in A. Okay, so if you still remember how to do this, so probability for your x, the number of tries that you needed for your first success, is greater than 3, is basically equals to 3 times failure. Then only you can have trial more than 3 times. So 3 times of failure, meaning Q3 will be equals to 512 over 1331. So what is your Q? Your Q will be cube root 512 1331. So you will get your Q as 8 over 11. So how to find your P? Your P will be equals to 1 minus 8 over 11, which gives you 3 over 11. Alright, okay, then after that you can move on. So you can use two ways, so depends on which one you like to use it. So yeah. Okay, so this is the first way. So meaning since I want to find 2, 3, right, then I'm going to use x smaller than 3 to minus off p, x equals to 1. Then I'm finding 2 and 3. So for this one, then I'll get this one, use the information that given in the question. Then I'm going to minus px equals to 1 is basically p, so that's why 3 over 11. So it will give me 456 over 1331, which is basically 0.343. Okay, or if you don't want to use that, then what you can try to do is p1 x smaller than 3, then it will be equals to px equals to 2 plus px equals to 3. Okay, so when you expand it, you should be able to get the same value as well. So please try to work it out yourself. Then I think you should be able to get, okay, I'm writing everything lah. Okay, 3 over 11, then 8 over 11 plus 3 over 11 plus 8 over 11 square. Then after that, I have 24 over 121 plus 1292 over 1331. Then it will give me exactly the same answer as above. Okay? So I think for this time, my example actually go through like pretty quick. So I hope that you can understand everything and so on. So after that, please move on for your past year question and exercise. Alright, okay, thank you.